Hello everyone and welcome to another Würth Elektronik webinar. My name is eiSos and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today is how the output capacitor can cause instability of a power supply. Our speaker today is Elisa Falco. Elisa, cool to have you here. Welcome. Before we start with the presentation, I would like to give you some more information. You will be muted during this webinar. This means that you cannot ask us questions via your microphone, but you have the opportunity to ask your questions into the chat. And then, after the presentation, Elisa will answer them. The presentations will be about 1 hour long, and after that, we make a short Q&A session and we'll answer your questions. If we are unable to answer all your questions within this time, Elisa will answer them via email in the next days. So last information from my side, you will all receive the link to the presentation as well as to the recording in the next days. So now I will hand over to Elisa and I wish you an exciting webinar.
So thank you very much, Silas, for the introduction. My name is Eleazar. I'm application engineer at Würth Elektronik. And as Silas mentioned, we will be exploring in this webinar how the output capacitor can cause instability of a power supply. The main points in the agenda will be the following. We will start by reviewing some of the basic concepts of feedback loop stability of DCDC converters. Then we will move on to analyzing the plant transfer function of the voltage mode buck converter, which will be used as the reference topology for the study. Here, we will focus the analysis on the role of the output capacitor and the effect of the variations of its parameters on the plant characteristic. After this, we will go through some example design cases with real measurements, which will show how a change in the output capacitor can easily make the control loop unstable. And we will understand what actually happened in the control system to reach that scenario. Finally, we will see a compensator design approach, which can ensure a stable control loop for a wide range of output capacitors, and that without having to redesign the compensator every time. However, this comes together with some important drawbacks and risks, which we will also cover. And then we will conclude with the questions and answers section. So let's start by reviewing the basic concepts of control loop stability in the case of switching converters. Starting with the typical blocks of a power supply with its control loop, we have the power stage, whose transfer function depends on the topology used, like buck, boost, flyback, etc. But not only this, it also depends on the operating mode, be this discontinuous conduction mode or continuous conduction mode. The voltage conversion of the power stage is controlled with the duty cycle of a PWM signal, which is provided by the duty cycle generator block here. This block and its transfer function changes depending on the control method used, like voltage mode, current mode, etc. These two blocks form the plant transfer function of the system, HS, which is also known as control to output transfer function. Then we have the compensator circuit with its transfer function, CS. It receives the output voltage signal from the power stage at its input, and it outputs a control signal to the duty cycle generator. And with this, we have our closed loop system. The compensator is designed based on the plant characteristics so that to ensure that the loop is stable and with high enough margins, since the power stage is designed and its components are selected to meet other requirements, not just to handle the power conversion, but also to do so with high efficiency, low cost, and in a small size, for example. And here we have a buck converter with a voltage mode controlled duty cycle generator and an op-amp based type 3 compensator circuit, which, as we mentioned, will be the reference configuration used. The basic blocks can be readily identified with the plant here and the compensator block here. And this is the equivalent control system diagram for AC signals. The compensator is in fact an error amplifier with negative feedback to correct for variations in the output voltage. The reference is used to set the DC output voltage, and for AC signals, it behaves like a virtual ground. If we consider a sinusoidal perturbation on the output voltage, this will be inverted by the negative feedback of the amplifier, which is equivalent to a 180-degree phase lag. If after going through the compensator and plant, its phase is lagged an additional 180 degrees or more with its amplitude unchanged, which is equivalent to a gain of 1, then a sustained oscillation has been created and the system is unstable. The product of transfer functions of the compensator and plant is known as the open-loop transfer function, and the stability criteria is taken from the open-loop frequency response. The frequency at which the magnitude of the open-loop transfer function equals 1, so equivalent to 0 dB, is known as the crossover frequency, and it is at this frequency that we will check the amount of phase lag for stability. For this, we are assuming that the magnitude curve only crosses over 0 dB once, which represents most cases and all the results which will be shown in this presentation. Now we need to understand how we will be measuring the open loop response in our converter so that to check the stability margins while the converter is actually operating in closed loop. And for this, the voltage injection method is widely used, and it will also be used in the measurements shown here. For more details, down here is a reference you can consult in this regard. We will simply use a low value injection resistor, so around 10 ohm, which will be connected between the output voltage and the compensator circuit as shown here. A differential sinusoidal signal is injected across the resistor terminals with a vector network analyzer while sweeping its frequency. And we observe the signals at points A and B with reference to the same point, any virtual ground in the circuit. We can see that in this measurement, we cannot separate the inverting action of the error amplifier from the compensator transfer function. So we will be looking for the phase at crossover to be actually higher than minus 360 degrees instead of minus 180 degrees. And in the way the phase is plotted, it will be read with reference to 0 degree, as we will see next. To complete this short review, let us see an example of our real measurements of the frequency response of the plant in red, the compensator in blue, and the open loop in black. Here on the left, we can see the magnitude curves, and after a closer look at the open loop response, we find a crossover frequency of around 21 kHz. Here we have the corresponding phase curves. We read the phase of the open loop response at the crossover frequency with respect to 0 degree, which in reality represents minus 360 degrees, as we mentioned before. And we find the phase to be around 60 degrees, which is equivalent to a phase lag of 300 degrees. The system is stable, and this 60 degrees is our phase margin. We can also see here how the magnitude and phase curves of the open loop response are just formed by adding the respective curves of the plant and compensator in these body plots. After this short review, let us move on and analyze the role of the output capacitor and its parameters on a voltage mode buck converter. For the analysis, we'll consider the converter operating in continuous conduction mode. The output capacitor is part of the power stage connected right across the output voltage terminals, and so it will contribute to shape the frequency response of the plant. In this case, the plant transfer function has the following structure in the Laplace S-domain. We can observe three different factors in this expression. First, a constant term, independent of frequency, called the low frequency or DC gain, which just depends on the input voltage and the amplitude of the sawtooth waveform used in the voltage mode duty cycle generator. Then we have the so-called ESR0, which solely depends on the output capacitor main parameters. This is its ESR and capacitance values. And finally, we have a resonant double pole, a term whose characteristic is also affected by the output capacitor parameters. Now, to get a good insight on how these three different factors help to shape the plant response, we will analyze them separately in the next slides. The DCO low frequency gain is just a constant gain term, not providing any phase shift over the entire frequency range. Of course, this is only true when considering an ideal op-amp, which is what we are doing here, and we can see an example of its body plot for a DC gain of around 21 dB. And this is the frequency response of the ESR0, which is placed at 18 kHz here. We see how the 0 provides a phase lead of up to 90 degrees 1 decade after the ESR0 frequency, and that the phase starts to change actually around 1 decade before the 0 frequency. Regarding the magnitude, the ESR0 is characterized by a rising gain slope at 20 dB per decade after the ESR0 frequency. And this is the frequency response of the double pole element, set here at a frequency of 3.4 kHz and with a quality factor of around 1.7. The response resembles that of a second-order LC filter, and that is in fact what this element represents, the resonance between the power inductor and output capacitor in the buck converter power stage. It shows the typical peaking around the resonance frequency, whose amplitude depends on the quality factor Q, and a gain roll-off of 40 dB per decade afterwards. Regarding the phase, it provides a phase lag of up to minus 180 degrees, and the rate of change of the phase around the F0, so the double pole resonance frequency, also depends on the quality factor. So higher quality factor, higher rate of change of the phase, and vice versa. As shown here, this element is also affected by the output capacitance and the ESR of the output capacitor. Adding the magnitude and phase curves of each of these three elements, we obtain the body plot of the plant transfer function of the buck converter. And we can see here the contribution of each of the three elements together, which in this example corresponds to the buck converter specification shown here. We can see how in the low frequency range, the plant response is dominated by the DC gain. Then the double pole appears, starting to roll off the gain at minus 40 dB per decade and pushing the phase down towards minus 180 degrees. However, it does not reach that value because the ESR0, which is placed at 18 kHz, here counteracts the action of one of the poles, and that results in a gain roll-off of 20 dB per decade after the ESR0 frequency, and the phase curve heading actually to minus 90 degrees instead of minus 180 degrees. Now we have seen so far how the output capacitor parameters affect the ESR0 and resonant double pole over a wide frequency range. But the frequency range of interest is that around the crossover frequency of the open loop transfer function, which is where stability will be determined. For a voltage mode buck converter in CCM, it is recommended as a rule of thumb to select the crossover frequency higher than 3 times the double pole frequency, and at the same time lower than 1/5 of the switching frequency. In the case of this example, this results in a range between 10 kHz and 100 kHz as highlighted here. We remember we had a switching frequency around 500 kHz and the double pole frequency was around 3.4 kHz. Let us see now how changes in output capacitor parameters influence the magnitude and phase curves of the plant response within the target crossover frequency range. For the same converter specification as before, we can see here the plant curves obtained with a fixed ESR of 10 milliohms, but different amount of output capacitance. 22 microfarad in red, 100 microfarad in black, and 330 microfarad in gray. For 22 microfarad, the ESR0 is at over 700 kilohertz, and it does not really affect either the gain or the phase in the range of interest. The double pole is at 11 kilohertz. For 100 microfarad, the ESR0 is at 160 kilohertz, and we can see how it affects the phase curve, but just a little bit above 50 kilohertz, but not the gain curve. The double pole has now moved to a lower frequency of around 5 kilohertz. For 330 microfarad, the ESR0 is now at 48 kilohertz, right within the frequency range of interest, and it substantially shapes the phase curve in this area. The double pole has moved to an even lower frequency with the increase in capacitance, as we will expect, and it is now at 2.8 kilohertz. We can see how the ESR0 has some effect in the gain curve in the range close to the 100 kilohertz, but rather low. What we can see is a large variation in both the ESR0 position and the double pole frequency, with just a small variation in the quality factor, which changes from 1.6 to around 2.1. And it does not have much influence in the frequency range of interest. Now, in this frequency range, we can see a magnitude difference of up to 25 dB in the lower end of the range, so here, while the phase difference is up to around 60-65 degrees in the higher end of the range, around 100 kilohertz. We also observe how the gain difference is caused by the shifting in the position of the double pole, while the phase difference is strongly influenced by the changing ESR0 position, while the double pole variation has almost no influence in the phase in this case. So we can see that a moderate change in output capacitance can cause a considerable change in the plant response of the converter around our target crossover frequency. Let us do now the same exercise, but fixing the output capacitance to 47 microfarad and considering different common values for the ESR. In this case, 10 milliohm in red, 100 milliohm in black, and 300 milliohm in gray. And here we can see the different plant responses obtained. For an ESR of 10 milliohm, the ESR0 is at 340 kilohertz, and again, it does not affect much the gain and the phase in the target frequency range. The double pole is at 7.5 kilohertz. For an ESR of 100 milliohm, the ESR0 position is reduced by a factor of 10 and moves down to 34 kilohertz, while the double pole frequency stays almost unchanged at 7.2 kilohertz. The lower ESR0, which is now closer to the double pole position, has a big influence in the phase curve, as we can see here, while to a lesser extent on the gain curve. For an ESR of 300 milliohm, the ESR0 moves now lower to around 11 kilohertz, and the double pole change is again negligible, as it just shifts slightly down to 6.7 kilohertz. We can see how the double pole and ESR0 positions are very close together in this case, and as the ESR0 cancels the effect of one of the poles, this results in an equivalent single pole first order response, with the gain rolling off, and we see the gray curve at 20 dB per decade, and the phase actually not diving but stabilizing, flattening at around minus 90 degrees. So we have a large change in ESR0 position while a moderate change in the quality factor, which changes from 0.9 to around 2.1, and the double pole frequency, whose change is also negligible. The gain difference is up to 18 dB at 100 kilohertz, as we can see here, while it is negligible in the lower end of our frequency range of interest. However, the phase difference that we can observe is up to 90 degrees, and this is over the entire target frequency range for the crossover frequency of the open loop response. And this is only caused or mainly caused by the change in the ESR 0 frequency. Okay, let us see now some real design cases showing how changes in the output capacitor can easily make the control loop unstable. We will start with an example of the impact of the bulk capacitor. Here we consider a very common specification for a 20-watt buck converter supplied from a 12-volt rail and providing 5-volt output. The switching frequency is 400 kHz, and this 4.7 microhenry MAPI inductor is a good fit here. Let us consider a requirement to keep the output voltage ripple in steady-state operation below 0.5% of the output voltage, which corresponds to 25 millivolts. The amount of output capacitance required for this is calculated in this expression as around 22 microfarad. Note that here we are neglecting the ESR contribution to the ripple, as we will be using MLCC capacitors. We can search and select a suitable part with RedExpert, and in this case, we will go with this 10 microfarad standard MLCC capacitor, which has an ESR of 2 milliohm at the switching frequency of 400 kHz and a very small DC bias drop at 5 volt. We will parallel 3 of them to get an equivalent capacitance of 28 microfarad with an equivalent ESR below 1 milliohm. This will be enough to comfortably meet the specification, and we will refer to this combination as CO1 from here on. Let us now consider that we need to meet the following transient response requirement, in which a load current step from 1.5 to 3.5 amps at 1 amp per microsecond should not cause the output voltage undershoot to exceed 100 millivolts. The transient response is also affected by the bandwidth of the feedback control loop, which we will select at around 20 kHz, as it will be shown in the next slide, but we advance it here. With this, the expression proposed in this reference gives an approximate value of the required capacitance to meet this specification, and in our case, this is around 160 microfarad. Again, we use RedExpert to find a suitable capacitor, and we find this small hybrid polymer type to be a good fit, with a capacitance of 220 microfarad and a low enough ESR of nearly 20 milliohm at 20 kHz. In this case, this capacitor acts as an energy reservoir for transient events, and it is commonly known as the bulk capacitor by this function. We will refer to it as CO2 for reference moving forward. Here we have the measured magnitude and phase curves of the plant transfer function of this voltage mode buck converter. We find the ESR 0 at 50 kHz and the double pole frequency at 4 kHz with a mild quality factor of around 1.2. The target crossover frequency range is between 15 to 80 kHz, and we select 20 kHz as we mentioned in the previous slide. And these are the magnitude and phase values of the plant response at 20 kHz. With a target phase margin of 60 degrees, the compensator needs to provide a phase lead of 116 degrees, and for such amount of phase lead, a type 3 compensator circuit is necessary. The design of this type 3 compensator goes beyond the scope of this webinar, but here again, I provide you with a good reference for compensator circuit design if needed. Setting these compensator component values, the following frequency response of the compensator circuit is measured. It provides a gain and a phase lead at 20 kHz, which are very close to the target specification. And with this plant and compensator, this is the open loop frequency response which was measured, with a crossover frequency of 21 kHz and a phase margin of 58 degrees. The gain margin is also high at around 25 dB. And this is the buck converter prototype board, which was used for the measurements, where we can see the output capacitor CO1, the 3 MLCCs in parallel, and the bulk capacitor, the hybrid polymer CO2, highlighted here. And here we have the load transient results. The original requirement is comfortably met, even with some headroom, showing an undershoot of 75 millivolt, which is lower than the 100 millivolt limit that we had. This is because we used a bit higher capacitance for CO2 than the value calculated, so we used 220 microfarad instead of just 160 microfarad. Now here we can see the impedance curves over frequency of CO1, the 3 MLCC capacitors in black, CO2, the hybrid polymer bulk capacitor in gray, and then we have the output impedance of the converter in closed loop operation in red. And this was obtained via a SPICE simulation. Now we can divide this into 3 different frequency ranges. The first range is below the crossover frequency of 20 kHz, and here the converter output impedance is much lower than the impedances of CO1 and CO2, as we can see here. And this is because the control loop has a gain in this lower frequency range, bringing the total output impedance of the converter to a very low value. Then we find a second range between 20 kHz and around 300 kHz. And we can see that in this area, the converter output impedance is actually set by the impedance of the bulk capacitor CO2. And this is because its impedance is lower than CO1 in this frequency range, and the control loop does not have enough gain above the crossover frequency of 20 kHz. As we move higher in frequency, above 300 kHz, which is here, and this is where the impedance curves of CO1 and CO2 intersect, now we can see that the converter output impedance is actually set and determined by the 3 MLCC capacitors by CO1, since the impedance curve of CO2 has now flattened due to its higher ESR value. From this, we can see that the output voltage ripple at the switching frequency, which is 400 kHz, is influenced and set by CO1 and not by the bulk capacitor, CO2. So if the design is reused or the transient requirement is relaxed at a later stage, then the bulk capacitor could just be removed to save cost. However, after removing CO2 and powering up the converter, this is what we find. The output voltage oscillates. We measure a frequency of around 40 kHz, but in the measurement with the cursors, we are actually skipping the distorted peak here in between. So the actual real oscillation frequency is 80 kHz. The amplitude of the oscillation is very high at around 500 millivolt, and what is not shown here is the erratic behavior of the converter, and this is characterized by enabling and disabling switching randomly. But during the time intervals in which it operates, it actually keeps the output voltage to 5 volt, but with the high amplitude distorted oscillation shown here, which has nothing to do with the switching frequency of 400 kHz, obviously. Now, we cannot measure the loop in these conditions, but amongst other options, we can use SPICE simulation to confirm that this behavior is really due to instability of the feedback loop. Here we can see the LT SPICE circuit with the output stage of the buck converter and the type 3 compensator, and we are using the average PWM switch model in voltage mode control, which eliminates the switching transitions. I have referenced here this book, which provides good guidance on creating such average models in SPICE. Here we have the simulation results of the transient response. We can see an oscillation at 75 kHz with an amplitude of 550 millivolt. And aside from the absence of distortion in these results, this is in fact in good agreement with the experimental results that we show in the previous slide. We now run an AC simulation to obtain the open loop frequency response using this schematic setup shown here. And this is something that we can still measure in LT-Spice even if the loop is unstable. And here is the result. We read a crossover frequency of around 85 kHz, very close to the oscillation frequency of 80 kHz that we measured experimentally. And the phase margin is negative at around -6 degrees. And this confirms that this behavior is caused by an unstable feedback control loop. So how did the planned frequency response change after removing the bulk capacitor so much to make the control system unstable? Now we can see here the planned response for both cases, with the bulk capacitor in black and without the bulk capacitor in red. The ESR0 is at around 50 kHz when using CO2, the bulk capacitor, but it moves to over 8 MHz when having only the MLCCs CO1. And in that case, it has absolutely no influence in the frequency range of interest. We can also see how the double pole frequency moves from 4 kHz with the bulk capacitor to a higher 14 kHz frequency with CO1 only, while the quality factor increases from 1.2 to 2.5, which we can see from the peaking of the two responses. So we remove the bulk capacitor, then the planned response changes in a way where it has now higher gain for frequencies higher than around 5 kHz, and with the compensator 1 fixed, this shifts the crossover frequency of the open loop transfer function to a higher value. As we have seen, it moved from 20 kHz to around 85 kHz. Now, in that higher frequency area, we can see that the plant without the bulk capacitor CO2 has around 50 degree more phase lag, as the ESR0 is no longer there. As we mentioned, it moved to above 8 MHz. On top of this, we also need to consider that the compensator provides the maximum phase lead at 20 kHz. And at 85 kHz, its phase lead will be lower. So overall, they both combine to push the phase margin from a comfortable 60 degree to a negative value, making the control loop unstable, as we have seen. So to make the control loop stable again without the bulk capacitor, we need to redesign the compensator. Now, for the planned characteristic with CO1 only. And here are the compensator components values selected. And this helps to obtain a similar crossover frequency and phase margin than in the original specification. Here we can see the transient response, which although it is stable, it suffers from a much higher undershoot of 520 mV, as there is not enough capacitance for energy storage after removing the bulk capacitor CO2. This is around 7 times higher undershoot than before, as we had only 75 mV before. However, we were expecting that, so this is not a surprise. Let us go now through another design example. In this case, we will be exploring the impact of a rather common occurrence during a design cycle, which is the need of a part-to-part replacement with the same capacitance but equal or better ESR. Here we will use the same base specification as in the previous case, with the only difference of a lower output voltage of 3.3 volt instead of 5 volt. This means we can still use CO1, the 3 MLCC capacitors in parallel, to attenuate the output voltage ripple. Now, regarding the transient response, we will use this aluminum electrolytic capacitor, for which Red Expert shows an ESR of 75 milliohm at 30 kHz, which will be our target crossover frequency, as we will see later. We will refer to this capacitor as CO3 moving forward. We follow the same procedure as before. We check the plant response and then design the compensator, in this case for a target crossover frequency of 30 kHz with a phase margin of over 50 degrees. And with these compensator component values here, we measure this open loop frequency response. The crossover frequency meets the target as it does the 52-degree phase margin as well. The gain margin is also acceptable at 15 dB. And here we can see the transient response with an undershoot of around 85 millivolts to a load current step from 1.2 to 2.7 amp at 1 amp per microsecond. It shows a little overshoot, but nothing important. So we have now a stable feedback loop, but as it is not uncommon during the development cycle, the requirements might be adjusted and changed at a later stage. Or maybe the design might just be reused for another product with the same functional requirements, but different other constraints. These are, for example, a change to an old surface mount component designed to optimize production, new mechanical constraints, stock availability issues, or just for trying to reduce cost. Let us consider in our design example that we have a new requirement. In this case, all components must be surface mount with a maximum allowed height of 4 millimeters. Now, ignoring the PCB headers on the board, this only affects the electrolytic capacitor CO3. After a new search in RedExpert, we can find a suitable part-to-part replacement. In this case, an H-chip polymer capacitor with a height of only 2 millimeters, the same capacitance value of 220 microfarad, but a lower ESR of around 6 milliohm, which should actually come as an advantage. We will refer to this H-chip capacitor as CO4 moving forward, and we will replace CO3 with it to meet the new requirement. Now here we can see the prototype board with CO1, the 3 MLCC capacitors to attenuate the output voltage ripple at the switching frequency, then CO4, the H-chip polymer capacitor, and CO3, the aluminum electrolytic capacitor. Note that this is only for reference since CO4 and CO3 will not be used at the same time on the board. And this is the measured open loop response after replacing CO3 by the H-chip polymer capacitor CO4 at 2.5 amp of load current. We see how the crossover frequency has dropped to around 18 kHz, and although the reading shows a phase margin of nearly 3 degrees, we can see there is a small dip in the phase curve here. So the real phase margin will be somewhere between 5 and 8 or 10 degrees. We can see also that the curve here appears more noisy than before, and this is only due to the reduction of the injection signal to the minimum possible so that we can actually measure the frequency response in these conditions. Otherwise, we get problems with overload. So now the system we can see is now on the brink of theoretical instability, but now we might wonder if the converter can still operate properly in these conditions. Now let us see. Here is the result of applying small load current steps of 150 milliamps. So this is from 2.15 amp to 2.3 amp at 1 amp per microsecond. We can see that the step-up transient to 2.3 amp that we show here, that results in a decaying oscillation, whereas the step-down transient from 2.3 to 2.15 amp results in a permanent oscillation, and this is actually what we are zooming in here, the step-down transient. In fact, In these tests, it was found that for low currents above around 2.2 amps, the oscillation decays and eventually disappears, whereas it remains for currents below around 2.2 amps. We also realized that the measured oscillation frequency of 17.5 kHz corresponds closely to the crossover frequency of the open loop response that we measured in the previous slide of 18 kHz, if we remember. Now let us see more results. When we power up the converter at 1.2 amp output current, this is what we observe. In this case, we are not using averaging acquisition in the oscilloscope, but normal acquisition. And we can see that because we can see the small output voltage ripple at 400 kHz running on top of this oscillation. And furthermore, we can see the voltage spikes which happen during the switching transitions. Now, the oscillation frequency that we observe is around 16.5 kHz, what we measured, and the amplitude is around 150 millivolts. And this is riding on top of the 3.3 volt output voltage. You can see here the legend on the left. Now, if we apply now a low current step under this condition, for example, to 1.9 amp, then the converter will enter into erratic behavior, randomly enabling and disabling switching. And we can see this behavior here. If we look closer into one of the intervals where the controller is operating, which is zoomed in here, we can observe the same oscillation at 17 kHz and with similar amplitude as before. Obviously, the converter cannot be of any use in these conditions, and from the oscillation frequency measured, which is again around the 18 kHz crossover frequency of the open loop response, which we saw before, we know this behavior is caused by an unstable control loop. So in which way could just this moderate ESR difference change the plant characteristic enough to cause this unstable behavior? Here we see the measured plant response with the electrolytic capacitor CO3 in black and with the H-chip polymer capacitor CO4 in red. In the first case, the ESR 0 position is at 9 kHz, whereas in the second case, the lower ESR of the H-chip polymer pushes the ESR 0 around 10 times higher at 100 kHz. We can see from the curves that the double pole frequency and quality factor are very similar in both cases, as the main influence on these elements comes from the capacitance, as we saw in the analytical results earlier in the presentation. After replacing CO3 with CO4, the faster roll-off of the magnitude curve causes a lower gain above 10 kHz, which for the fixed compensator circuit means that the crossover frequency will shift down. And this is exactly what we found as it moved from 30 kHz down to around 18 kHz. Regarding the phase, we can see how the shifting of the ESR 0 to 100 kHz causes around 35 to 40 degree higher phase lag in the area of the new crossover frequency. This, together with the lower phase lead provided by the compensator below 30 kHz, caused the phase margin to collapse, leading to the unstable behavior we just observed in previous slides. But as before, a compensator redesign taking into account the plant characteristic with the H-chip polymer capacitor CO4 will just solve the issue. And with these compensator component values, we measure the following open loop response with a crossover frequency of almost 30 kHz and a phase margin of 55 degrees with a gain margin of around 25 dB. And here we have the transient response with the new compensator. We measure an undershoot of around 45 millivolt, which is lower than the 85 millivolt which we measure with the electrolytic capacitor. This is despite having the same capacitance and similar crossover frequency and phase margin both solutions, the lower ESR of the HC polymer capacitor helps to improve the transient response as we were expecting at the beginning. At this point, one might be wondering whether there exists a design approach which can keep the control loop stable despite a wide variation of output capacitance and ESR values, and that without having to redesign the compensator every time a change is made. Okay, let us see. Here is the frequency response of the plant for the design example cases considered so far in the presentation. CO1 only in red, so the 3 MLCC capacitors, CO1 plus CO2 in gray, with the hybrid polymer capacitor, and CO1 plus CO3 in black, with the aluminum electrolytic capacitor. Note that the solution with the HC polymer, CO4, is not shown as it has the same capacitance and similar ESR than the hybrid polymer capacitor CO2, and that leads to an equivalent result. Now we can see how in the frequency range below 1 kHz, the plant response is dominated by the low frequency gain, and there is practically no effect of the ESR0 and resonant double pole elements, as this happens at a higher frequency. We can see that in this range, the gain is constant and the plant provides little to no phase lag. So what if we skip that rule of thumb of crossing over after the double pole frequency and just cross over below 1 kHz instead? Then stability could be ensured for a wide range of output capacitors without having to redesign the compensator. Let us see this option in more detail. In this case, as the plant does not contribute any phase lag, a type 1 compensator circuit can be used, instead of the type 3 that we used before. A type 1 compensator is just an integrator circuit built around an op-amp with C1 and R1 as shown here in the image. The compensator provides high DC gain to reduce the steady state error, but it does not provide any phase lead, so it has a constant phase lag of minus 270 degrees. And if the plant does not provide any further phase lag, then we should achieve a phase margin of 90 degrees. The frequency response of the compensator is shown here on the right. For the design, as the resistor R1 is used together with the resistor R low to set the output voltage to 5 volts in this case, then we can calculate the value of the capacitor C1 to offset the low frequency gain and achieve a target crossover frequency around 1 kHz, as it is shown here. And for this, a value of around 15 nanofarad will be required. And here we have the measured magnitude curves of the open loop response for each output capacitor solution with our newly designed type 1 compensator. Note how they all cross over at around 1 to 1.2 kHz here. And here on the left, on the right, we see the phase curve results. The phase margin stays above 80 degrees for the cases of CO2 and CO3, and nearly 90 degrees for the case of the MLCC capacitors only, so CO1 only. The slightly lower phase margin with the bulk capacitors is because there was a small phase lag of the plant, still at 1 kHz, due to the lower double pole frequency, which was caused by the much higher capacitance of the bulk capacitors. But still a very high phase margin in all cases. And this despite the large difference in capacitance and ESR values, especially compared to the solution with CO1 only. This is the transient response for the solutions with the two bulk capacitors, CO2 on the left and CO3 on the right. The load step applied is only 1 amp at 1 amp per microsecond slew rate. Observe how they are stable, but despite the smaller low current step as compared to the previous test that we've shown in the webinar, the transient response suffers from a longer settling time and higher undershoot as before. So we read here minus 174 millivolt, and we had before 75 millivolt, and here around minus 160 millivolt compared to the 85 millivolt we had before. There is also a small but well-damped oscillation in the case of CO2, which is almost not appreciable in the case of CO3. We can see it here. Now, we know that CO2 has a lower ESR than CO3, so this was around between 15 and 20 milliohm, while CO3 was around 70 milliohm. So this is a good insight right before we see what happens in the case of CO1 only. This is the transient response of the option with only the MLCCs without bulk capacitors. Despite the very high phase margin of almost 90 degrees, there is an underdamped oscillation in the response. It has a frequency of around 14 kHz. And if we revisit the frequency response of the plant with CO1 only, we will realize that this actually corresponds to the double pole frequency, which represents the resonance between the power inductor and the output capacitor of the power stage of the buck converter. In this case, due to the lower capacitance and much lower ESR of the solution with only the MLCC output capacitors, the quality factor is rather high at 2.5. But why did we not observe this before when we selected a crossover frequency higher than the double pole frequency, as it was recommended? Well, considering that the bandwidth of the control system in closed loop is approximated as the crossover frequency of the open loop response, then we can see that the system does not have gain above the crossover frequency of 1 kHz. This means that any resonance which happens above the crossover frequency cannot be corrected by the loop. If these resonances are well damped, so a low quality factor, then there will be no problem. But if not, ringing will appear, and this is exactly why it was recommended to select the crossover frequency around 3 times higher than the double pole resonance frequency. However, in addition to the degradation in the transient response speed and higher undershoot, we must be aware that in the case of a very high quality factor, actually the peaking here of the magnitude could actually cross over the 0 dB line more than once, and that could make the control loop unstable altogether. So this approach makes the control system very robust against variations not only in the output capacitors, but also in the power inductor. But as seen, this comes at the cost of a worse transient performance, and the best results will be achieved with a redesign of the previous Type 3 compensator. So let us see what are the key takeaways and a short summary of what we have seen in this webinar. So first, we have seen how the output capacitor parameters shape the converter transfer function of the plant and the frequency response, and these parameters are the capacitance and its ESR values. For a fixed compensator, so any changes in the output capacitors will affect the stability margins. Now, the consequences of this might be just transient performance degradation, but even full-blown instability, as we have seen. So it is recommended to always check the feedback loop stability margins after any changes in the output capacitors are made. And redesign the compensator to keep good stability margins, even if you don't need it to ensure stability. It is good to have high stability margins. Now we have seen that if we select a very low crossover frequency, then we can ensure stability for many different types of output capacitors and even power inductors with different inductance values and DCRs. However, this comes at the cost of a degraded transient response and oscillation ringing for high quality factors. And out of this, we can see how a compensator tailored to a specific plant characteristic will always provide the best performance and should be our preferred approach. So thank you very much for your attention. Now, if you have any questions, please feel welcome to ask, and I will try to answer.
Yeah, thank you, Eleazar, for your presentation. Now we'll come to your questions. I see we have a lot of questions, so now we start with the first question. If you design the compensator for stability without a bulk capacitor and then you add it, does the converter turns unstable in the same way or not? Should the phase margin not be higher when you have the ESR 0 at a lower frequency?
Okay, so this is something that in the examples which are shown in the webinar, I actually measured, but I didn't show here, didn't include in the presentation, but there is an application note also coming out and all the results will be included there. However, I can say that yes, that's correct. When you design the compensator for example, for CO1 only, the 3 MLCC capacitors, and then you add the bulk capacitor afterwards, meaning the ESR, now you have the ESR 0 providing some phase lead in the target crossover frequency range area, and also some higher gain. I found that so in the case of in the first design case that we saw with the hybrid polymer, then the phase margin went down to around 50 degrees. So in that case, you didn't really have to redesign the compensator. I did the same exercise also in the second example with the aluminum electrolytic capacitor and the HC polymer. So after stabilizing the converter for the HC polymer capacitor, then replacing it with the aluminum electrolytic capacitor, that actually I measure a lower phase margin of around 30 degrees. I mean, that's quite low, so that should be recommended to redesign the compensator to get a minimum phase margin, a worst case of 45 degrees, which is the rule of thumb which is normally recommended. Now, this was just in the cases shown in this presentation, but I have also done other measurements from experience, and in some cases I found that the phase margin was actually higher. It went from around 60 degrees to around 80 degrees or higher. And so it is correct. You will assume that when the ESR 0 moves to a lower frequency, then you have higher phase lead, but you should also take into account the compensator response, which in this case is not constant. So depending how you have designed the compensator circuit, if you have used the K factor or you have designed it manually, then it will be different. In the K factor, you know that the maximum phase lead happens at the target crossover frequency, and the phase lead which provides at above and below this crossover frequency will be lower. Okay, so you will expect a lower phase margin actually if that phase, that lower phase is actually much lower than what the ESR 0 is providing. But that is not always the case. You can also design the compensator in a different way. So I will recommend that you don't assume that it will always be fine. I recommend that you always check it because you might find some surprise there. I hope this answers the question.
Thank you. Then next question. If you're using a few bulk capacitor in parallel instead of only one, what happens to the control to output transfer function? How do you analyze it?
Okay, thank you for the question. Right, here in the presentation and in the transfer function, so you might have seen we have only considered one capacitor which actually shapes the frequency response of the plant around the target crossover frequency. either CO1 when we used it alone, the 3 MLCC capacitors, or the bulk capacitor. Whenever we have used the bulk capacitor, we found that this capacitor is the one which shapes the magnitude and phase curves of the plant transfer function in the target crossover frequency range. Now, when you have more than one bulk capacitor and they have different capacitances and ESR, and they are in parallel, they have similar impedance in the frequency range of your target crossover frequency of the open loop transfer function, then the analysis gets more complicated. In this case, the transfer function that we show, that only assumes one capacitor. If you want to analyze or to obtain the plant transfer function with more than one capacitor, and the important thing here is that they have different capacitances and different ESRs, you will find that the transfer function actually has new elements added to it. So the best approach that I will recommend, and up to 2 different capacitors in parallel, I think the analytical approach might be fine. But higher than that, if you have, I don't know, 3 or 4 different capacitors with different capacitance and ESR, I would recommend to go for the SPICE simulation approach. And you will see, and you can quickly check this in a SPICE simulation, how when you have these different capacitors, how the plant response has actually changed. You no longer has only one ESR 0, but you have new elements. Don't want to go into details here, but SPICE simulation will be the best approach.
Thank you.
Okay.
Then, one last question. What happens in other topologies like boost, forward, and flyback?
Well, I guess this is related to how the output capacitor affects the plant transfer function of other topologies, not just the buck converter as we saw. So more than the difference in topology, we need to look at the duty cycle generator, so the control method we are using. In this case, we have seen voltage mode control, and in reality, if you use a boost converter or a flyback converter in voltage mode control, you will still have that resonant double pole. Now the difference comes when you use current mode control. Current mode control, you no longer have that double pole at the resonant double pole, but you have a dominant pole, what is called dominant pole. And this pole is the one which happens at the lowest frequency. And that's why it is called dominant pole. Now the frequency of this pole also depends on the output capacitance. And that is how the output capacitor will actually affect these converters when you are using actually current mode control. But not just the boost or flyback, but the buck converter itself. So current mode control will change the plant characteristic itself. Now, the ESR 0 is always going to be there for all converters, but I will say this, the main difference is how it affects the other element. In this case, the double pole in the case of voltage mode control, or the dominant pole when you are using current mode control. I hope that answered the question, provide some insights. Thank you.
Thank you. Then I would say we are finished with our session of today. When you have any more questions, you can write into the chat, and then Eleazar will answer them via email in the next days. So now, thank you, Eleazar, for your presentation and for the answers of the questions. And yeah, thank you for your attention. I hope you enjoyed it, and hopefully we see us on our next webinar. And yeah, thank you and goodbye.
Goodbye.